Coming up. Let's continue. Okay. Yeah, we're very glad to have everyone here for our session on differential operators in algebraic geometry and commutative algebra. So our first speaker today will be Daniel Levcovitz, and he'll give us a survey on d-simplicity.
Okay. Thank you, Luis. Thank you, Jack. I would like to thank the organizers. And it's a pleasure to me to be here. Okay. So I will start showing my slides. So this will be a survey on the simplicity. Okay. So I will work always over a field K of characteristic 0. And let's recall the definition of a K derivation of a commutative K algebra. It is an endomorphism of the additive group that satisfies that annihilates K and satisfies a Leibniz rule. Okay. The set of all K derivations I will denote by this, and everybody knows this is naturally an R module. Okay. The basic example, the prototype example of derivations are the usual partial derivatives in a polynomial ring over K. Okay, these are simple examples of derivations. So let's move now to the simplicity. So you take now any commutative K algebra and a K derivation. We'll say that an ideal is D invariant or D stable, or simply a D ideal if D applied to I is contained in I. So the derivation D stabilizes the ideal I. And we say that the ring is D simple if the only D ideals are the trivial ones. Of course, these are always the trivial ideals are always D ideals. If there is no other one, we say that the ring is D simple. I want to generalize this a little bit. Instead of taking just one derivation, take a family of derivations, finite or not. We say that ideal is D stable if dy is contained in Y for all D. And of course, the trivial ideals are D stables. If the ring has no other D stables, we call it D simple. And are differentially simple if the subset is just the whole set of derivations. Okay. Just one observation. Note that if Y is a D ideal, then you can induce the derivation on the quotient ring, just as the usual way. Okay. I want to say something about this condition here. This condition has a geometrical interpretation. In the case, for example, suppose that your algebra is the affine ring, the affine coordinate ring of an affine variety over some in some affine space. So whenever you have a derivation of the coordinate ring, actually what is happening geometrically is that you are giving a field of tangent vectors on that variety. Okay, and to say that an ideal is stable means that the ideal will correspond to a subvariety, an algebraic subvariety that is tangent in every point to the field of vectors that you gave. So to say that the ring is this simple means that there are no algebraic subvarieties. So you have a variety, you have a field of tangent vectors on that variety, and to say that the ring is this simple is exactly to say that there are no non-trivial, no proper subvarieties of that big variety that is tangent everywhere to the field of vector fields. Okay, this is the geometrical meaning of these and of this. Okay. So let's give a few examples of simple derivations. The simplest example is the simplest example is the polynomial ring in one variable, and you take this derivation here. Then this ring is simple just because every ideal here is principal, so generated by one polynomial, and when you derivate it, the degree of the polynomial will decrease. So therefore, the polynomial won't be in the ideal anymore. So this is okay. Now let's move to the ring of polynomials in two variables, and you maintain the same derivation, ddx. Now this ring is not the simple anymore, because the ideal generated by the other variable is stable, because you just apply it and get 0. Okay. By the way, just an observation to test if an ideal is stable, you just have to test in a set of generators of that ideal, and this is very easy and is a consequence of Leibniz rule. Okay. Okay. The first, as far as I know, the first example of a simple derivation in the ring of polynomial in two variables was given independently by George Bergman and Yves Lejean, and is this one. This one is a simple derivation of the ring of polynomials in two variables, and I will show you why in a moment. Okay. Let me give you at least one example in three variables. This was given by Collier-Coutinho around 1990. So it's this derivation here with these coefficients, and you have these technical conditions here, and this ring is this. Although it is difficult to give examples in polynomial rings of simple derivations, nowadays we have a lot of them, even families. Okay, let me show you a nice result of Shamsuddin. Suppose that you have a commutative ring that contains the rational, and there is a simple derivation of R. So you want to extend this derivation to the polynomial ring in one variable. You can extend the derivation putting any polynomial here, but here you have a degree 1 polynomial. Okay. So Shamsuddin proved that this extension is simple if and only if this differential equation does not have any solution. So this is the link between simple derivations and differential equations over rings. Okay. So as an application, let's show that why Bergman and Lejean example is simple. So you start with the polynomial ring in one variable, take the simple derivation here. We know that this is simple, and I will extend it like this. So dy is just this 1 plus xy, and note this is a degree 1 polynomial in y. Okay. So the differential equation associated to this derivation is this one. And it's kind of easy to see that this has no solution in the polynomial ring in one variable, because the right side increases the degree. while the left side decreases the degree. So it's a kind of difficult problem. We don't know how to classify simple derivations, even in the case of the polynomial. Okay? It seems to be very, very difficult. The only known case is when n is 1, and so all the simple derivations are just scalar multiples of the usual one. Okay. But there is a nice result of Yves Lecan that such that that says when a Shamsuddin derivation is simple. What is a Shamsuddin derivation? A Shamsuddin derivation is a very particular class of derivations of the polynomial rings. They are of this type. So this coefficient is 1, and the other coefficients are degree 1 in the variable, and the coefficients are just so these are called a Shamsuddin derivation. Okay. And owing to a very nice paper of Lecan, we can decide effectively if a Shamsuddin derivation is simple or not. Not all Shamsuddin derivations are simple, but you have an algorithm that you apply to all these polynomials in one variable, and at the end, what you'll have is that the derivation is simple or not. I will prove this. I will. Now, I want to show you an application of simple derivations to commutative algebra. And this is a very nice also result of Seidenberg of 67. Now you consider a finitely generated algebra over K, which is a domain. So this is what we call also an affine domain, right? And recall that we say that it's differentially simple if there are no non-trivial ideals that are stable by all derivations, that is, they are stable by the whole module of derivations. And Seidenberg proved that R is differential simple if and only if R is regular. Or say that is so geometrically speaking, this is more or less intuitive because suppose that R is the coordinate ring of an algebraic variety, and the algebraic variety has a singular point. Then this point will correspond to a maximal ideal. Let's suppose that the base field is algebraically closed. So this point will correspond to a maximal ideal that will be fixed by all. That will be stable by all derivations. Okay. Okay. This is the result of Seidenberg. But Bob Hart in 75 proved that. Nevertheless, Bob Hart showed that even if this is differential simple, that is, it is regular, there need not exist a particular derivation such that this is the simple. So remember that differential simple means that it's simple by all derivations, by the whole module of derivations. And the example is this one. Is a rational sphere. Of course, this algebra is regular, so it's differentially simple by Seidenberg. But Bob Hart showed that this does not admit a single derivation such that it is the simple. So, but he proved that in the local case, this is true. So suppose that R now is a localization of an affine ring, an affine domain over a maximal ideal. Then this ring is regular if and only if there exists a derivation such that R is the same. So then it comes to a very nice problem, I think. This is the problem of K-simplicity. So it follows from the result of Seidenberg that a regular affine algebra is always differential simple with respect to a finite family of derivations. For example, we can take D to be the set of generators. In the affine case, this module is always finitely generated. And you can take, for example, any set of generators, okay? So let us call a K algebra or K differential simple if it is differentially simple relative to a family with exactly K derivation. Exactly K derivation. In particular, if this module is free, for example, of rank dimension, for example, suppose that R is regular, for example, and suppose that is regular and the module is free, then it is differential simple with this K here. Okay. However, this is not the smallest K. For example, polynomial ring in n variables over a field of characteristics is always D simple. So it always one differential simple, while its full dimension is n. Okay, so thus, when one may ask, given a differential simple algebra, what is the smallest positive case, K, such that R is K differential simple? For example, for the ring of polynomials, this integers is just 1, because in the polynomial case, you can always find a D simple. But in this example of Bob Hart, it is not 1. It's not 1. It is 2, because the dimension of the ring is 2. So we prove with Coutinho that if X is a smooth, complex, irreducible variety over the complex number, then its coordinate ring is too simple. So you need only 2 derivations, okay? And here we need the complex because we use transcendental methods to. And I observed that this bound is sharp because it was proved by Archer in his PhD thesis, 1981, that if you take a smooth curve in C3, which is not a complete intersection, and these objects, they do exist, then this is not the simple for any D. So but it will be too simple by our results. Okay. Okay. So now I want to speak very briefly about the isotropy group of a derivation, which is the topic I've been working recently. So the whole group of automorphisms of R acts by conjugation in the module of derivation. Just given one derivation, you can conjugate it and you get another derivation. And moreover, D is simple. It's kind of easy to see that if and only if this is simple. So we are interested in the isotropy group. This is the isotropy group of this action. So it's just the automorphism that fixes the derivation. Okay. So René Balthazar, in his thesis, doctoral thesis, that René was a student of Ivan Pan, who will talk here on Monday, and he investigated the isotropy group of a simple derivation, a simple Shamsuddin derivation, and that is a derivation of this form, and he proved that this group is trivial. Okay, and he also calculated the isotropy group of a non-simple derivation. This one is non-simple, and you see he got infinite group here. So René and Invan conjecture that let there be a simple derivation of finitely generated K algebra, then its isotropy group is fine. And so a bit later, Mendes and Pan prove a very nice result. Suppose that K is an algebraically closed field of characteristic 0 and D be a simple derivation, not necessarily Shamsuddin, because Balthasar result is Shamsuddin, but here you don't have to suppose that Shamsuddin. Then its automorphism, the isotropy group is 3. Okay. This is sharp because this is very mysterious to me, because it works only in dimension 2. Because when you increase the dimension, for example, we have this derivation, if n is greater or equal to 3, and this derivation is simple. This was proved by David Jordan in 1981. But its isotropy group contains all these translations, and since we are working over a field of characteristic 0, this is an infinite group. Okay, so Mendes and Pan is very specific to dimension 2. So, and just to finish my talk, we generalize Bertoncello. Luciani Bertoncello is a student of mine, we were able to prove that if for Shamsuddin derivations, then if it is simple, then its isotropy group is 3. But the converse of this result is still conjecture. So thank you very much. I apologize for going a little bit over. Thank you. Thank you. Thank you.
Great. Thanks a bunch for the nice talk. Are there any questions?
So can I ask something? Does the definition of Shamsuddin derivation depend on the coordinates? And if not, is there a coordinate-free characterization?
Depends on you have to separate one coordinate. One coordinate is very special.
I see. Thank you.
Yeah, you can change coordinates, but very, very carefully.
Thanks.
Depends.
So I had a question that might be a bit naive. There are singular rings, affine rings, which, according to Seidenberg, they're not stable under the action of the derivations, but they are stable under the action of differential operators. And I was wondering if there is any sort of analog of Hart's theorem in this setting. Can you sometimes find a single?
No, not that I know. No,
okay.
No.
Okay.
Of course, it's very nice to think about to be able to use higher order differential operators.
Mm.
Not that only order 1, that are essentially order 1. Okay?
Right.
And but I don't know about that. I don't know about that.
Okay.
Yeah.
Okay.
It would be nice to investigate derivation, stable ideals under higher order differential operators.
Mm.
Even to work on over fields of positive characteristics, because when you work over field of positive characteristics, everything fails, because suppose that your field has characteristic P just in one variable, and you take the ideals generated by x to the P. This will be ddx stable. But maybe if you use Hasse-Schmidt derivations,
Right.
So the whole set of hashes between this. So that will be interesting to investigate. But I don't know anything about in positive characteristics. But it's possible to ask and to investigate that.
Great, thanks. Are there any other questions? If not, maybe we can thank Danielle again.
Thank you. Thank you.
And are you ready to go, Giuseppe?
I need to share my screen, probably.
Great.